Okay, hello Discrete Math. We're just going to do this whole homework on induction. Here we go, this is number 2. I think I did this with really bad handwriting in one of the 2 periods. I think maybe it was period 8. But okay, on the whiteboard everything's going to be kind of more beautiful. So let's go. This is, I would call, kind of an easy induction problem. This is something we could have done probably just in Pre-Calc C. Because it's an equality, so nothing really kind of creative is required. I need to prove that this equals this. It's not obvious to me that this is true at all. Although I guess this is like a geometric series or something. So maybe I could use a formula for that or whatever. But okay, let's not assume any background stuff. Let's just do it. What do we have here? I have this left-hand side, which I'm going to nickname A sub n, and I have this right-hand side, which I'm going to nickname B sub n. And so, what I would like to prove is that A sub n equals B sub n for all n. That's the real claim. How am I going to do it? By induction. So, what is the sort of first n for which this makes sense? I think even built into the problem, it says that n should be greater than or equal to 0. Okay, well then let's just check out what is that base case when n equals 0. Well, when n equals 0, it's a little bit weird because if n equals 0, then I'm adding, you know, from k equals 0 to 0. Maybe this is not so hard, but technically speaking, you know, a sub 0 is the sum from k equals 0 to 0 of negative 1/2 to the k, which is therefore just the sum of one term. You know, k only gets to be 0, and so it's negative 1/2 to the 0. Okay, so it's just 1. On the other hand, what can I say about b sub 0? Well, b sub 0 is just 2/3 plus 1/3 times negative 1/2 to the 0. But negative 1/2 to the 0 is just 1, so this is 2/3 plus 1/3, so this is also 1. And okay, therefore the theorem is true for the case when n equals 0. Okay, and now I'm ready, I guess, to do the inductive step. So let's do the inductive step. I make my inductive hypothesis. Inductive hypothesis, suppose that it's true for some n. So suppose A sub n equals B sub n, you know, for some arbitrary n greater than or equal to 0. And now what I need to do is I need to show that it holds for the next number as well. Show that the property is inherited from one number to the next. Okay, well, I just begin. What is A sub n plus 1? It's just going to be what I get when I perform this summation, but instead of stopping at n, I'm going to stop at n plus 1. So it's just the sum from k equals 0 to n plus 1 of negative 1/2 to the k. And okay, since I want to relate this as much as possible to my inductive hypothesis, then I kind of want to make this a sub n plus 1 look like a sub n. Well, in fact, it's a summation, so the sum of the first n plus 1 terms is just the sum of the first n terms, you know, plus another 1. Therefore, this really just is the sum from k equals 0 to n of negative 1/2 to the k, so in other words, the first n terms, and the n plus first term is just what you get when you raise negative 1/2 to the n plus first power. Okay, cool. No, that's it. You just pull off that last term basically. All right, so what is that? What have I sort of showed then? I've showed that a sub n plus 1 is just a sub n, that's what this is after all, plus this one extra number, this negative 1/2 to the n plus 1. But then I make use my inductive hypothesis. The inductive hypothesis is that the formula works for n. And so if the formula works for n, then a sub n equals b sub n, and so I sort of perform a kind of replacement now with these two expressions. Okay, and right, what is b sub n? It's that. And so here's where I am right now. I have 2/3 plus 1/3 negative 1/2 to the n, that's just b sub n, plus negative 1/2 to the n plus 1. And now all the work remains in showing that this is b sub n plus 1. Okay, well let's just simplify it and maybe it will just all just kind of come out. Here I kind of want to combine these two. So I'm going to just say that this is 2/3 plus, well, 1/3 negative 1/2 to the n plus, what does it mean to raise negative 1/2 to the n plus 1? Well, it's just like there's a negative 1/2 and then there's, you know, the rest of the negative 1/2s. And now I can factor here and I get 2/3 plus 1/3 minus 1/2 is just like negative 1/6. So I guess I'll just write that as negative 1/6, negative 1/2 to the n. Basically factoring out a negative 1/2 to the n. I think this is pretty clear. I'm left with the 1/3 minus 1/2, which is negative 1/6. Okay, but I don't want it written like that. I want it written like 2/3 plus, I want to rewrite negative 1/6 as 1/3 times negative 1/2 times negative 1/2 to the n. Okay, and what is this? Squeezing this in here, this is 2/3 plus 1/3 times negative 1/2 to the n plus 1. In other words, it is exactly b sub n plus 1, which is which was the goal to show that. And so, if you want to be super awesome now, you say something like a sub 0 equals b sub 0. That's the base case. And what did we show? We showed for any n whatsoever that on the assumption that the formula held for n, then it holds for n plus 1. That's the inductive step. So by induction, I guess we can just say, so by induction, in fact, a sub n equals b sub n for all n. It's true for 0, and whenever it's true for a number, it's true for the next number, so therefore by induction it's true for all numbers. Okay, good. Pausing this, coming back in a second to do more. Okay, number 8. This one was slightly exciting because they didn't give you the formula. And so they didn't give you the theorem that you were actually trying to prove. They said, find a pattern, discover the formula, prove that your formula is correct. So that's like, real math or something. But actually, I think this problem is not that hard, though I do have to, notice some things or I don't know what. So I didn't even prepare this or review this or anything, though I have done this problem before, so I think the answer will just come to me. I'm going to just temporarily call this a sub n just for clarity so I can refer to it as something. Alright, what's a1? Well, a1 is 1 times 1 factorial. 1 factorial is just 1, so this is just 1. Alright, what's a2? I'm just hoping a pattern will emerge. a2 is 1 plus 2 times 2, so 1 plus 4, okay, so that's 5. What's a3? Right, well, it's going to be 5 plus whatever 3 times 3 factorial is, and that's 6 times 3, that's 18, and so this is 23. Maybe I'm seeing a pattern, maybe I'm not. What's a 4? Interesting. A 4 is 23 plus 4 times 4 factorial, whatever that is. What is 4 factorial? Well, 1 times 2 times 3 times 4, so that's, that's 6 times 4 is 24. So it's 24, yeah, 24, but then times 4, so it's 96. 96 and 23 is 119. Right, did I do that right? 96 and 23 is 119. Alright, so hopefully you are now seeing a pattern, but if you're not, you just gotta keep on going until you see that pattern. What is A5? Well, it's gonna be 119 plus 5 times 5 factorial. Oh man, 5 factorial is so big. What is 5 factorial? 1 times 2 times 3 times 4 times 5. So it's 2 times 3, so 6 times 4, 24 times 5 is 120. So that's 120 is 5 factorial times 5 is 600. So I guess that's like 719. Wait, I think I see what's going on here. 5 factorial is 120. Whoops. 4 factorial is 24. 3 factorial is 6. And so it seems that these numbers are each 1 less than the next number factorial or something like that. Yeah. So I think I'm ready to give my conjecture. My conjecture is that at any given point, when I add all these up, what I get is just n plus 1 factorial minus 1. I think that's right. Let me just double check that. Plug in 3, yeah, 4 factorial is 24, yep. Plug in 4, I get 5 factorial, 120 minus 1, yeah. So I'm now like very confident or something that this is the right formula. I can't remember if there was some deeper way of figuring this out. I mean, there surely is some way, but maybe this is best kind of deep proofs with understanding and stuff are best left to next next unit. Yeah, I got nothing to say. Okay, so maybe now that you've found the pattern, maybe now the proof is actually kind of easy. I bet it is. I've already done the base case. I've already checked that it works for n equals 1. In fact, I've just checked that it works for the first 5 numbers. So now I'll just make my inductive hypothesis. Let's just like do this like super fast. Inductive hypothesis. You can use k, but you don't have to. Let's just say that it works for n. And now what I need to do is to show that it works for the next number. And maybe we'll arrive at some understanding from this. Well, what is a sub n plus 1? It's just, it's 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus all the way up to n times n factorial plus n plus 1 times n plus 1 factorial. In other words, it's just a sub n plus the last number that you added, which was n plus 1 times n plus 1 factorial. And okay, what is a sub n? By assumption of my inductive hypothesis, it's b sub n. And so when it comes to doing the proof, here we go, those two are equal, and hopefully now this thing just does itself. What is b sub n? It's n plus 1, n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. And I guess what I'll do is just factor out an n plus 1. What am I doing? Minus 1. Did I do that right? B sub n is n plus 1 factorial minus 1. That's n plus 1 times... Sure, that's right. Of course it is. Yeah. What? Well, okay, I guess let's just start. So I factor out an n plus 1 factorial, leaving me with 1 plus, n plus 1. And then there's still this minus 1. The minus 1 I just leave there. And of course that's just n plus 2. So this is n plus 2 times n plus 1 factorial minus 1, but that is just n plus 2 factorial minus 1, and that is just by definition b sub n plus 1, and so we're done. Okay, I thought that was pretty easy. Good to be back in a minute. Hello. Here we go, number 13. I did this in period 9, but maybe not so well or something, I don't know. Theorem, every integer n can be written in the form n equals 5a plus 7b for some integers a and b. Okay, well, let's not think about this too much. Let's just kind of dive in. We're supposed to be doing this by induction, I suppose. So let's do it by induction. I don't even know where to start. Maybe take the case n equals 0. Can you think of two integers a and b such that 0 can be expressed as a linear combination of 5 and 7? Well, yeah, because 5 times 0 plus 7 times 0 is 0. Alright, so it's certainly true for n equals 0. Perhaps that was a silly place to start. Now let's try for n equals 1. Can you think of two integers a and b which yield which yield 1? Yeah, I guess we can, right? 15 minus 14 seems to work. And so 5 times 3 plus 7 times negative 2. Well, indeed I have found a and b. In this first case, my a and b were 0. In my second case, in my second example, n equals 1, a is 3, and b is negative 2, and 15 minus 14 is indeed 1. So okay, it seems to be working there. Maybe I'm ready to just continue. Yeah, so, okay, how did I know that this was going to work? Well, I'll tell you why I knew this was going to work, because of Bezout's identity. Bezout's identity says, you will recall, that the GCD of two numbers, I don't want to use a and b now, let's just use, M and n or something, that the GCD of two numbers, m and n, is, or can always be expressed as a linear combination of those two numbers. So s times m plus t times n. And so with that kind of in the back of our mind, then it's not surprising that I can express 1 as a linear combination of 5 and 7, because the GCD of 5 and 7 is 1. So, by Bezout's identity, there should be some way of expressing 1 as a linear combination of 5 and 7, and here it is, right? 5 times 3 plus 7 times negative 2 is 1, and so it works. Okay, so at this point you might be thinking, well, this is just silly, because if 1 is expressible as a linear combination of 5 and 7, then so must any number. Give me some number that you want, I don't know, 10 or something. Well, just multiply both sides of this equation by 10, and then that just kind of does it. So I don't know whether that's deep or silly or something, but I'm just going to do the proof. So here's my inductive hypothesis. My inductive hypothesis is, suppose that, and maybe this has value, so suppose that n, maybe I want to even use sort of more careful language, right? Suppose for, arbitrary n greater than or equal to 0, that there exists a pair of numbers, a and b, such that n can be written as 5a plus 7b. That's really what we're assuming. And if I can express n in the form 5a plus 7b, I now have to show that I can do that with n plus 1. Well, just take n plus 1. What is it? It's just n plus 1. Therefore, it's 5a plus 7b. Here I refer to the a and b that I assume exist for this case, for my inductive hypothesis. And okay, then just like, plus 1. So that's n plus 1. But then that's just 5a plus 7b. Now I use the fact that 1 is just 5 times 3 plus 7 times negative 2. And what do I get now? Well, I get that this can be expressed as 5, a plus 3, plus, and here the coefficient of 7 is b minus 2. And so indeed, I have expressed n plus 1 as a linear combination of 5 and 7. A plus 3 is an integer, b minus 2 is an integer, and so that sort of does it. Yeah, that's all I got for number 13. Okay, be back in a second for the next one. Okay, number 15 says show that n factorial is less than n to the n for n greater than or equal to 2. Alright, this is not totally obvious fact, but which I think is kind of important. Alright, we do it. How? By induction. Let's check out the base case. The base case is when n equals 2. Is this true when n equals 2? Well, is it true that 2 factorial is less than 2 squared? Yeah, that's just true, because 2 is less than 4. Alright, I now make my inductive hypothesis. Inductive hypothesis is that n factorial is less than n to the n, for some arbitrary n greater than or equal to 2. And now, from this assumption, I shall show that this property holds for the next number, which is to say that n plus 1 factorial is less than n plus 1 to the n plus 1. Alright, so this kind of thing is hard, the first couple times you do it because you might not know where to begin, or maybe it's never hard, I don't know. What should we do? Well, I have a system. My system says try to make things look as much like your inductive hypothesis as possible. So what I'm going to do is I'm going to take this thing that I'm trying to prove. Well, what is this thing I'm trying to prove? N plus 1 factorial, blah, blah, blah. Well, what is n plus 1 factorial? It's just n plus 1 times n factorial. And what is n plus 1 to the n plus 1? It's a product of a whole bunch of n plus 1s. How many? N plus 1 of them. So I could write this as n plus 1 times n plus 1 to the n. And I like to be very careful and continue writing the word show at every step, just to remind myself that I haven't proved this yet. This is just the thing that I want to prove. Alright, well, just for simplification purposes, I guess I can divide both sides by n plus 1. And so it suffices to show that n factorial is less than n plus 1 to the n. This is now what I need to do, so I'm sort of working backwards, I suppose. Alright, well, this is now very clear because, look, here is my inductive hypothesis. So this is what I know to be true. And this right here is the thing that I need to prove. So this is what I need. I need this thing in the purple box. And okay, so how can I get from here to here? There are sort of many ways, but ultimately I need to show that n to the n is less than n plus 1 to the n. That is my wish. Why is this my wish? Because if this were true, then I could say that n factorial is less than n to the n, which I know, which in turn is less than n plus 1 to the n, and therefore by transitivity I get the thing in the purple box. Okay, and so what can I say about this wish? Well, yeah, it's just obviously true, and exactly how much more we write here is maybe up for debate. Why is this true? You could divide both sides by n to the n, and you can get something that's equivalent, which is just this. Is this true? Yeah, it's just true that a number bigger than 1 raised to some positive integer power is also bigger than 1. So I'm going to take that as a kind of low-level basic property of arithmetic and stop there. You could do maybe more induction or something like that to show that this is true, but I'm just going to kind of call it a day. And by call it a day, I mean when I go to do my proof, which is now, here's what I'm going to do. I'm going to say, okay, make sure I do this right. I have my inductive hypothesis. What's my inductive hypothesis? It's that n factorial is less than n to the n. Okay, great. What else do I have? Well, I have that, make sure I do this right. I have that 1, so now I just begin with just like a math fact, right? That 1 is less than 1 plus 1 over n for positive integer n. That's just true. And this is just n plus 1 over n. And now I'm applying the number fact, which I'm not going to justify, which is that if I have a number that's bigger than 1, then if I raise both sides to the nth power, then that inequality is preserved. So if you raise 1 to the nth power, you get 1, but here, if we have n plus 1 over n to the nth power, then that has to be bigger than 1. Okay, that seems fine to me. All right, well, splitting this up and moving things over, that tells me that n to the n is less than n plus 1 to the n, and that was indeed my wish. Why was that my wish? Because if I take my inductive hypothesis and this little fact, which is almost doesn't need to be proved at all, then I have that n factorial is less than n to the n, which is less than n plus 1 to the n. And so, by transitivity, n factorial is less than n plus 1 to the n. And now, I multiply both sides by n plus 1, and that gives me that n plus 1 times n factorial is less than n plus 1 times n plus 1 to the n. In other words, n plus 1 factorial is less than n plus 1 to the n plus 1, and I'll just stop there. That is the property that I was trying to prove for the case when, well, I've showed that on the assumption that the property holds for n, that it must hold for n plus 1, and so we're good. Alright, back in a second. Alright, let's go. Hello, number 16. This is kind of hard, but maybe like not in a fun way, maybe just in an annoying way, I don't know. It depends on your personality. I did this problem with a bunch of students during the virtual check-in Wednesday. But anyway, we should kind of just do it right now and see what happens. This is the kind of problem that I would have assigned in Pre-Calc C, but I would have labeled it very hard and would not have expected almost anyone to get it. But now we're in discrete math. You gotta be able to like do this stuff. Here's some incomprehensible sum of reciprocals of square roots or something like that, and apparently that's bigger than this. Alright, if you want to be like a mathematician, you gotta be able to crank out proofs of facts like this. And I want to be a mathematician one day, so I better do this proof. Alright, well, for purposes of clarity, I will nickname the left-hand side of this A sub n, and the right-hand side of this B sub n. And so, what I want to do overall is I want to prove that A sub n is greater than B sub n for all n greater than or equal to 1. Alright, let's check if it's even true for 1. So, base case, n equals 1. What do I get? Well, let's see. What am I supposed to do? I'm supposed to start with 1 and I'm supposed to keep going until n is 1. Alright, well that's a little bit silly because when n is 1 it's just 1. So in other words, when n is 1, this left-hand side is just 1. And when b is 1, then when n is 1, what can I say about b? So b1 would be, alright, well I plug that in, and what do I get? 2 times root 2 minus 1. And already it's just not totally obvious to me at all that 1 is bigger than 2 times root 2 minus 1. So there's some sort of work to do here, even to just establish that this is true for the base case n equals 1. Well, is it? I don't know. Let's find out. If I divide both sides by 2, then I get 1/2 is bigger than root 2 minus 1. If I add 1, I get that 3/2 is bigger than root 2. I think it's a... I don't think I needed these fractions actually. Why don't I just change my mind, multiply this out, so I get to 2 root 2 minus 2. Yeah, this is better. Add 2 to both sides, that gives me that 3 is bigger than 2 root 2. Is that true? Yes, it is true, because these are two positive numbers, and if I square them, I get that 9 is bigger than 8. And so now, what you should really sort of say is, look, 9 is bigger than 8. And so the fact that 9 is bigger than 8 implies that 3 is bigger than 2 root 2, which implies that 1 is bigger than thing by subtracting 2 from both sides, which just implies the thing, and so we get the thing. Okay, so base case kind of done. Let's do our inductive step. So I'm going to make my inductive hypothesis. What's the inductive hypothesis? Well, it's that A sub n is bigger than B sub n, for some n greater than or equal to 1. Okay, and so what is, maybe it's worth it to write out the full kind of inductive hypothesis. What is it that I sort of know? I know that 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root n is greater than 2 root n plus 1 minus 1. And what is it that I need to prove to complete the inductive step? Well, I need to show that it works for n plus 1. So I need to prove that 1 plus 1 over root 2 plus 1 over root 3 plus all the way up to 1 over root n plus 1 over root n plus 1 is bigger than what happens when this formula, when you plug n plus 1 in for n in this formula. Okay, some people don't like that, which is why I sometimes like to switch to k, especially when I'm teaching beginners. But okay, you guys aren't beginners, so you can handle that. Set n to be n plus 1 thing. Don't cry over that. It'll be okay. So that's 2 root n plus 2 minus 1. Okay, that, I hope everyone agrees, is what needs to be shown. If I can prove that, then the inductive step is complete and the proof is over. All right, how am I going to prove this though? Well, you need to massage this proof statement until it looks sufficiently like the thing that I know. What I know is the inductive hypothesis, and ultimately, look, what is the left-hand side of this? It's just like it's just this, but like one more thing. So personally, I think it's simplest to just subtract this from both sides, or you could. There's a whole bunch of ways to do this. Maybe the simpler thing even is to just take the inductive hypothesis and add 1 over root n plus 1 to both sides. Maybe let's do that. And so what I sort of know is, continuing on the other side of the light switch, what I know is that 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root n. And now what I'm explicitly doing is adding 1 over root n plus 1 to both sides of my inductive hypothesis. So that's 2 root n plus 1 minus 1, but then plus 1 over root n plus 1. Okay, so just to be clear or something, I'm just going to throw in these blue parentheses here. Where did this line come from? It just came directly from my inductive hypothesis by performing just a little kind of algebra 1 maneuver. Okay, good. Well, now I may do a kind of a comparison. Here I have this thing that I really, really want to prove. This thing that I want to prove, this is my need. I need this to be true. And also, I have this statement here in purple. This statement I know to be true. I know it to be true because it's just one algebra 1 step away from my inductive hypothesis. And now I need to somehow get from the no statement to the need statement. How can I do it? Answer: with a bridging inequality. Give me a second to figure this out. I guess what I want to show is that this is bigger than this. Make sure I have that right. No, I had that backwards. I need to show that this is bigger than that. I think that's right. Because then is bigger than jump, so therefore, yeah. Good. So, what I wish were true, hopefully I don't mess this up, what I wish were true is that 2 times root n plus 1 minus 1 plus 1 over root n plus 1. I wish that that were bigger than 2 root n plus 2 minus 1. Why do I wish that that were true? Because taking what I know that this is less than this, and sorry, this is bigger than this. Oh man, kids are home. If that were also in turn bigger than this, then by transitivity I would get this is bigger than this, and that's exactly what I need. Okay, so I think this is a great way of sort of organizing yourself, and I hope I've now sort of convinced you that that if I can prove this wish, then the problem is over, because I have my inductive hypothesis. I have this purple box, which is basically my inductive hypothesis with one tiny extra addition. And if I can prove the wish, then the purple and the green combine to give me the red, and then I complete the inductive step, and then the proof is over. Okay, so I can now focus all my attention on just proving the wish. Is this wish true? I think it just is true. Let's show that it's true by manipulating it into something that's true. So I get 2 root n plus 1 minus 2 plus 1 over root n plus 1 is bigger than 2 root n plus 2 minus 2. Well, I can cancel the minus 2's. So I get 2 root n plus 1 plus 1 over root n plus 1 is bigger than 2 root n plus 2. Is that true? Not obvious at all yet. How can I simplify this a little bit? Well, just by principle of sort of get rid of fractions. If I multiply through by root n plus 1, that just seems like a good idea. So if I multiply through by root n plus 1, that gives me 2 root, well, I just get 2n plus 1 then, plus 1 is bigger than 2 root n plus 2 root n plus 1. Okay, continuing over here, what do I get? I get 2n plus 3 is bigger than 2 root n squared plus 3n plus 2. Is that true? Still not obvious, but getting closer. Here I now square both sides. If n is positive, both sides here are positive. So that gives me 4n squared plus 12n plus 9 is bigger than 4 times n squared plus 3n plus 2. Alright, I think I'm in good shape now, because I get 4n squared plus 12n plus 8. And so this whole thing reduces to 9 is bigger than 8. And since 9 is bigger than 8, I now add some stuff, factor, take the square root of both sides, which is allowed as long as everything is positive, sort of manipulate, divide, etc. Okay, I'm not even going to bother drawing in my double arrows because I don't feel like it, but since 9 is bigger than 8, then by following this proof backwards, up this bottom of the board here, I get the wish and I'm going to make the excuse that I'm lazy and I ran out of board space, so I won't rewrite everything, but I think it's clear that, that this problem is done. Alright, and I think I'm just going to stop this video now because we did 18, not super particularly well in both classes, but we did it decently in both classes, and so I won't include that in the video. Hopefully that helps some people. Goodbye.